Ah, okay, perfect. Yeah, Michael, thanks.
Thank you very much to the chairman and to the organizers, of course, for giving me the opportunity to present this work, which is a joint collaboration involving two institutes from the National Research Council, CNR SPIN and CNR IOM from Genoa and Trieste, the International School for Advanced Studies, SISA, here in Trieste, and the Physics Department in Genoa. And the focus of my talk is about the graphite ultra-low friction and superlubricity as probed in AFM experiments, mostly focused on the case of colloidal AFM probes. In this case, it is well known that when sliding on graphite, there is the formation of a nanometer thick transfer layer, which is formed by graphite flakes that are captured from the underlying substrate to the surface of the colloidal bead. And I give you insight on the morphology and quantum mechanics and also frictional properties of this nanometer thick transfer layer, mostly within the framework of the thermally activated Prandtl-Tomlinson model. If I have time, I also show you some preliminary results. So a few years ago, there were some very interesting experiments that basically restated the experiments originally proposed by Martin Dienwiebel and co-workers. So in this case, there was, however, not a nano-sized AFM probe, but a colloidal AFM probe that was sliding on a graphite substrate. And the authors, I report here data by Lee and co-workers, published in Advanced Science 2017. And the authors considered, in this case, a silica bead with a curvature radius of about 11 microns. It was smooth with a surface roughness below a couple of nanometers. And the authors observed pretty clear phenomenology. So at initial contact that was established under ambient conditions, the friction force had some finite value, and there was a linear relationship between the friction force and the normal load and the friction coefficient in the region 10⁻². And after what they call the pre-sliding stage, that basically consists to slide continuously over the graphite substrate, we observed at some point randomly, they said, a jump, a breakdown of the friction forces and also the friction coefficient down to the range of 10⁻³ or even less. And this was considered by them the signature of the formation of a transfer layer on the colloidal bead. And they characterized by high-resolution transmission electron microscopy the contact region of the bead with the graphite surface. They realized that there are multiple transferred few layer graphene flakes. And they suggest that the mechanism behind this superlubricity mechanism is basically a multi-asperity incommensurate contact. So the main idea is that on top of the pristine bead, you have some nano-sized asperities, and during the pre-sliding process, they are covered by randomly arranged graphene patches. And so you end up with this type of multi-asperity contact that is supposed to give rise to the superlubricity mechanism. So our idea was to try to give a deeper insight into the quantum mechanics and elementary dissipation for this type of system. So here are our own data. So we start with colloidal beads that were very comparable with the ones used by Lee and co-workers, so 12 microns of contact radius, surface roughness below 1 nanometer, so they are ideally smooth. And here in the top left corner, you can see the friction map that we record in the initial stage on graphite surface. So there is a clearly distinguished dissipative friction loop, and the lateral force is in the range of 100 of a nanonewton. And just at the beginning of this contact, you can also study the friction force versus normal load curves. So there is some linear behavior where the friction coefficient is small in the range of 10⁻², and there is a nonlinear part that goes down to the pull-off point where the addition is pretty high, usually in between 2 and 3 micronewton, and is due to van der Waals and capillary adhesion to the substrate. And after prolonged sliding over the surface, what happens randomly is that the friction loop gets fully closed, so the friction force is decreasing, and also the adhesion force is decreasing quite a lot, so we have a decrease of the contact forces by more than 1 order of magnitude. And in this case, also the friction coefficient goes down to 10⁻³ or even lower values. And as you can see here, the response of just the same bit is not reproducible. I mean, if you slide on different regions, you always interact with some unavoidable surface roughness, like due to the graphite surface steps. And in that case, you have a transition in these characteristics. But the friction force and the adhesion force always stay very small. We try to fit the nonlinear part of this curve with the Dirichlet-Miller-Toporov theory, and we realized immediately that the only way to have some reasonable interfacial energy in the range of 100 of millijoule per meter square and the shear stress around a couple of megapascal was to assume also breakdown of the contact area between the bead and the graphite substrate. That, so we assume, goes from the mesoscale, that is the initial contact size, contact radius 150 nanometers. It goes down to the nanoscale. And to have a deeper insight, we characterize the contact area of the beads repeatedly by reverse AFM imaging. And we observe that on top of the beads profile, there are some protruding tips that indeed correspond to a clustering of few layer graphene flakes that are captured by the underlying substrate. And the flakes have a lateral size in between 50 and 100 nanometers. The thickness goes from a few nanometers up to 10 or sometimes even 20 nanometers. And they preserve the lubricious properties of graphite, as you can see here in this reverse friction force microscopy map. This is a silica, and these are the graphite flakes. And so this supports the idea of a nanoscale contact area between the micrometric bead and graphite. And with the appearance of the transfer layer, and so the breakdown on friction forces, we also observe the multiple tip effects that appeared in AFM imaging that are again an effect, in our opinion, of the presence of these protruding superlubric tips. And we repeated the experiments with different colloidal probes in order to understand how the phenomenology varied with, for instance, the curvature radius that was varied between a couple of micron and 25 micron. And we consider different types of materials like borosilicate, glass, silica, titanium. Also, as you can see here, there are different types of surface roughness, from a random roughness to a globular one, some textured on titanium particles. And in each situation, we basically observed the very same phenomenology. So here reporting the friction force versus sliding distance, there was a sort of running in at the beginning when we used the pristine beads, and the force, the lateral force stayed, the friction force stayed in the range of 100 of nanonewton, and then there was a decrease, a progressive decrease of the friction as soon as this nanometer thick transfer layer formed. And in each case, we observed a decrease of adhesion also in between pristine state and transfer layer mediated condition. And also the friction curves show a friction coefficient in the range 10⁻³. We characterized by reverse imaging the contact area before and after the transfer layer formation. And in each case, we observed that the flakes basically provided an increase. The transfer layer provided an increase of the surface roughness. The red bars show how the surface roughness increases in the contact area after the transfer layer formation. So basically, the mechanism that Lee and co-workers suggest seems to work fine. So the flakes are basically captured by the highest asperities of the probe, and we are enhancing any morphological fluctuation within the contact area. And we tried to gain some insight on the contact mechanics, because the fact that we have some random roughness due to the transfer layer does not necessarily imply a multi-asperity contact. So we went back to the results, the scaling law arguments that have been developed by Pastewka and Robbins in the field of, in the framework of large-scale simulations for a sphere-on-flag contact geometry with a self-affirmed fractal roughness. And in this case, there is a scale. There are three different regimes that we can distinguish. There is a high load regime where we have practically a conformal contact between the sphere and the flat, so the surface roughness is not playing the bigger role. And then we have a multi-asperity contact in which the contact area scales linearly with the normal load, and then we have a single asperity regime in which the contact is basically dominated by the first nanoasperity that touches. And the parameter that drives the transition from the three different regimes is the ratio of the normal load to the critical load, where the critical load is the parameter that depends on bulk material properties like the Young modulus and the Poisson ratio, and also on interfacial properties like the interfacial energy or the self-affine fractal roughness through the local slope of the morphology. And we realized that in the case of our colloidal probe AFM experiments, also those reported in the literature, I would say this critical load varies in between 100 and 200 micronewtons. But experiments usually are carried out at loads definitely smaller than 1 micronewton. So the ratio normal load to the critical load is usually in between 10 to the -3, 10 to the -4. So I think that we are close to the onset to the crossover between a single asperity and multi-asperity regime. And the argument that, in our opinion, supports more strongest the assumption of a single asperity contact also in such experiments are our atomic scale friction data. So basically, all the junctions that we prepare, we were able to see atomically resolve the friction maps and with the lattice periodicity of graphite. And we observed usually a dominant stick-slip motion for all the junctions at sufficiently high load, let's say above 200 nanonewton. And we observed also friction duality. That means that for the very same junction, moving in different position or as a function of the working time, we observed transition from two different type of characteristics. Type 1 characteristics that are those in which the friction force is almost independent of normally applied load down to the pull-off point. And then type 2 characteristics in which there is an initial stage in which the friction force stays very, very small. And then at some point there is a sudden or a gradual increase of the friction force, with, of course, a very small friction coefficient, as you can see here. And we explored the friction loops related to type 2 friction curves, and we observed that there was a strong modulation of the friction loops with normal load going from almost continuous superlubricity sliding to stick slip with single or multiple slips. And this is a result that has been reported many times in the past in the field of single asperity contact mechanics. It can be remapped or studied by the Prandtl-Tomlinson model. And so what we made was basically to investigate our friction loops, analyze them, and replot in a master curve that reports the normalized friction force versus the Tomlinson parameter. And so the type 1 friction versus load curves, those that are more dissipative, are conditions in which we basically are here in the high the high values of the Tomlinson parameter, and the nearly continuous sliding relates basically to a situation in which the eta parameter was below 2. We repeated this type of analysis that supports single asperity contact mechanics, also for colloidal bits with different curvature radius, and as I can show you here, we observed the very same phenomenology, so friction duality, a strong modulation of the friction force with the normal load, and a reasonable agreement with the thermally activated Prandtl-Tomlinson model. So here the Prandtl-Tomlinson model are numerical solution to the Langevin equation that were studied at room temperature where the experiment was reported, and also at the sliding velocity about 30 nanometer per second of our experiment. So we can also appreciate that we are not fitting the athermal PT model, but we are more biased toward the thermally activated transitions. And as I told you before, friction duality, and as Michael observed also, friction duality has been reported in the past in many systems, especially originally by Dean Wiebel and co-workers, also in the nanomanipulation experiments at the mesoscale. So we suggest that, in our opinion, according to this data, the friction phenomenology that takes place when we have this nanometer thick transfer layer is basically a nanoscale competition. On one side, we have some superlubricity mechanism that gives us the ultra-low friction at the smallest loads and probably relates to incommensurate stacking at the contact interface. And then when we increase the load or when we have some dominance of defects, we have pinning effects. And in the pinning, we can, of course, have also contamination from ambient environment. And since I have time, I just show you some preliminary results that concern the possibility to prepare transfer layer not by tribo transfer, so by sliding the probes over graphite surface, but by using liquid dispersion of few layer graphene flakes. And there are now some available products, especially obtained by liquid phase exfoliation or other methods that provide high-quality flakes with a lateral size, few layer graphene flakes with a lateral size in the range of hundreds of nanometers. And we studied them in the past, and we observed that they have a friction response which is comparable in terms of shear stress with the high-quality few-layer graphene flakes obtained by mechanical exfoliation. And so we try to prepare the transfer layer by functionalization of the probes before sliding on graphite or the layered materials. So we start from a water-based dispersion, which is surfactant-free, and we deposit them by drop casting. And since the flakes are loosely attached most of the time to the surface of the bits, what happens is that when they are trapped in the contact area, you easily remove them from the contact area during the first sliding cycles of the surface, but sometimes you get the big flakes that stay attached in the contact area. In that case, we have low adhesive, low friction contacts, like in the Triboinduced material transfer case. We have a friction coefficient in the range of 10⁻3. Again, we are able to observe stick-slip atomic friction on hexagonal boron nitride, and also we are having now some results on molybdenum disulfide and hexagonal boron nitride. So in principle, we are able to exploit this approach to study heterojunctions. And the phenomenology, as I told you, is pretty similar with the Triboinduced case. So again, this is remarking the importance of having nano-sized graphitic tips at the contact between these probes and the substrate. So I come to the conclusions. So the main message is that, in our opinion, the lubricious and nanometer thick graphitic roughness, which is Triboinduced, is controlling the adhesion and the friction forces through the energy landscape, probably of the highest Triboinduced nanosperity. And we found that superlubricity can be described as a load control transition from superlubric to stick-slip sliding through a thermally activated Prandtl-Tomlinson model. And I would like to thank a national project from understanding and tuning friction through nanostructure manipulation, which is supporting these studies and also cooperation with some of you. So thank you very much.
Thank you. Thank you very much, Renato. Are there questions? Roland.
Thank you, Renato, for sharing these results. I was wondering how stable the observation of these little patches forming on the spheres is against materials. So if I buy any colloidal probe from some store and if I buy any graphite, would you expect it will work? Or is it sensitive to the graphite, to the actual sphere?
You mean with the flakes?
With the flakes?
Liquid dispersion.
Liquid is the one
Triboinduced, the Triboinduced layer. So about the stability of this layer, so we work with HOPG substrates. So we work with a conventional substrate, not with very small, not a very high quality ZFB was the quality, and Basically, we observed more or less always the same phenomenology, but about the size of these flakes, there was some scattering in this size. So depending on the probes, we observed sometimes smaller, sometimes larger flakes. This is something that was, in our opinion, pretty random, because somehow it depended also on the geometry of the probe before, of the pristine probe, before starting the experiments. And these transfer layers are pretty unstable, so they change from time to time when you are sliding over the graphite surface, and we found that the change was dramatic. I'll just show you here in a while, when we change the nature of the substrate. So what we made was to prepare the transfer layer on graphite, and then the same probe was placed in contact with other bike-layered materials. And we basically, there was no way, unless very few cases, to study reproducibly the superlubricity on this substrate, because there are a lot of effects, I think, that also the increase of the Young modulus of TMD materials or the increase of adhesion of these flakes, for instance, versus hexagonal boron and tride, basically cleans your contact area from these flakes. So yes, we are really unstable.
Okay, thank you. I think we should move on to the next speaker. So thank you, Renato.